Good afternoon friends and welcome again to Parijat sir classes. एक बार और आपका स्वागत है. And today as you can see that today I am going to start with you the electricity chapter number 2 which is the Kirchhoff's law. आज हम करेंगे today we will be starting the chapter number 2 which is the Kirchhoff's law, and already I have loaded this is chapter number 2 of the electricity. This is electricity chapter number 2, okay, class 12. So already I have uploaded the chapter number 1. Please go and see there. So it's my request that please keep following the Parijat sir classes and please see the updated notes. What I am providing here is the complete updated notes of the class 12 chapters, so you don't have to make any notes of your own, you don't have to write down any notes of your own, you don't have to create anything of your own. So everything will be provided here. So I would request you that please go through the things very nicely, and my request to you, all of you, is please like, share and subscribe my channel, so that I can create more and more videos for you. Okay, so without wasting much time, let me go forward to start the chapter which is the Kirchhoff's law chapter. So let's get started. So see, first of all, we are discussing here one of the most important chapters which is the Kirchhoff's law. So what is Kirchhoff's law? The algebraic sum of the currents meeting at a point or at a junction in a closed circuit is 0. That means total current meeting at a junction will be 0. For example, this is the junction. So in this junction, see, there is a current which is coming I3. There is a current which is going out I2. There is a current which is going out I1. Current going in I5, current going out which is I4. Okay, so the Kirchhoff's first law says that sum of the currents at a junction should be 0. That means, so let us assume that the currents which are entering the junction is taken as positive. Current which are entering the junctions are taken as positive, and the currents which are flowing away, the current which is flowing away from the junction is taken as negative. So I can write I3 is the current entering plus I5 minus I1 because it is going out, minus I2 minus I4 should be 0, because this was the Kirchhoff's first law. It has told that the sum of the currents at any junction should be 0. That means this should be 0. Currents coming in is positive, currents going out is negative. So from here I can say that this is my relation from the Kirchhoff's first law. Clear? Now what is Kirchhoff's second law? Kirchhoff's second law, it says that in a closed circuit, the algebraic sum of the potential, that means total sum of the potential, and the algebraic sum of the product of current and resistance. So this is the sum of the product of current and resistance. The total summation of this should be 0. This is the Kirchhoff's second law. Sum of the potentials in a closed circuit, sum of the product of the current and the resistance in a closed circuit should be 0, right? So from here, from here, see, there are certain points which I have discussed here. What is it? Kirchhoff's first law. What is the Kirchhoff's first law? First law was summation of the current at a junction is 0. So Kirchhoff's first law it supports the law of conservation of charges. Law of conservation of charges. Kirchhoff's first law supports law of conservation of charges. Kirchhoff's second law, it supports law of conservation of energy. Law of conservation of energy. So this is the second law. It supports law of conservation of energy. Now the third one, EMF is negative. Please watch here, that if this is a battery, if this is a battery, if this is a battery, if you are, EMF will be negative if we go from negative to positive. That means if you are going in this direction, negative to positive, your EMF will be taken as negative, and if you are going from positive to negative, your EMF will be taken as plus. Your EMF will be taken as a plus, right? Please, so this is the first some theory about the Kirchhoff's laws. So let us go more ahead and see. So applying the Kirchhoff's laws in some particular circuits. So let us see. Here we have taken a circuit, as you can see, that here is an EMF used E1, here is an EMF used E2. So this EMF E1 is sending current I1, as you can see it is sending current I1, and here is an EMF which is sending current I2. They meet here, and there is a current I3, there is a current I3. So I can easily tell that I1 plus I2 should be equal to I3. This is what I can tell, correct? Now let us apply the Kirchhoff's second law. So what was the second law? Second law says that sum of the potential difference and sum of the product of current and resistance in a closed circuit should be 0. Okay, total potential and total product of the current and resistance in a closed circuit should be 0. So let's apply here. So first of all, we are choosing the loop A, B, E, F, A. We are choosing this part of the loop A. We are choosing this loop A, B, E, F, A. So we are choosing this loop. We are choosing this loop. So now when we are applying the law, Kirchhoff's second law. So see, let us start from here. So this is, and please again remember one thing, that if you are flowing, if you are going in the direction of the current, in the direction of the current over a resistance, if you are going in the direction of current over a resistance, then that potential is taken as positive. That potential is taken as positive. And if you are going opposite to the direction of current, if you are going like this, let me show you. Suppose if you are going like this, you are going in the direction of the current, so the potential will be positive. And if you are going opposite to the direction of the current, the potential will be negative. The potential will be negative. Okay, if you are going opposite to the current, the potential will be negative. Now based on this, so let's see what is happening here. So this is the loop we have taken. Okay, so we are starting from here I3. So I3, see, we are going in the direction of the current, we are going in the direction of, so it is plus, this is plus. Now we are going I1, I1 is going in the direction, so this part is going in the direction of the current, in the direction of the current, so this is also plus. And now we are going minus to plus, we are going minus negative terminal to positive terminal. So I told you that will be taken as negative potential, so this is minus E1, and we have completed the loop, which is 0. Okay, so from here we get one relation. Second, we are choosing now this loop. We are choosing the loop A B C D E F A. That means we are choosing this loop A B C D E F and A. So this is the loop we are choosing, and now see how we are going. We are going in this direction. We are going in this direction. We will complete the loop in this direction. So let's see now. So first of all, if I go along E2, we are entering the positive terminal, so that is plus. Then we are going over this, we are going opposite to the current. So I will take it I minus I2 R3. Then we are going opposite to the direction of the current, in the direction of the current. So I will take plus I1 R1. Then we are going from negative terminal to positive terminal, so we will take minus E1, and that is the loop finished. Okay, so that is 0. So from here we are getting E1 minus E2 equal to I1 R1 minus I2 R3. So this is what we apply the Kirchhoff's laws, two laws. Okay, here we applied the junction law, and that is the first law, and here we are applying the second laws. Second, we will be discussing the numericals of this topic. So first of all, let us see how the applications of the Kirchhoff's law is being done. So we are discussing now another important component of the electrical part, that is Wheatstone bridge. Okay, so what is a Wheatstone bridge? It states that if four resistances P, Q, R, S, so here you can see P, Q, R and S, four resistances are arranged to form a bridge. So this is a bridge, we are using a galvanometer here, okay, with a cell E. This is the cell E, and a key K1. This is the key K1 between the points A and C, and a galvanometer is being used here. This is the galvanometer which we'll be using here. Okay, and a tapping key K2. So here we are using the tap key K2 between the points B and D, as you can see. Now what happens? First I will close the key K1. So current will start, and then I will close key K2, and then what we will see, let the current which is getting started, we will see that the current which is getting started from the EMF from the battery E, which is the current which is coming out from the cell E, let it be I. So see how the current is getting distributed. So from here, let us imagine that I1 current goes this side. So here on this part it will be I minus I1. Okay, now out of I1, suppose IG current goes on this side. So the current which will be coming to this part will be I1 minus IG. Is the current which is coming on this part. Okay, now IG current comes from here, I minus I1 current comes from here. They meet at this point, they add up, and it becomes I minus I1 plus IG, which goes on this direction. And when they meet, these two currents, when they meet, the net result is again I, which is returning back. Clear? So this is how the Wheatstone bridge actually works. Now what we have to do is we have to choose the values of P and Q in such a way, P, Q, R, S. We have to choose the values of P, Q, R, S in such a way so that there is no deflection in the galvanometer. There is no deflection in the galvanometer. And then the bridge is said to be balanced. The bridge will be said to be balanced. We will choose P, Q, R, S in such a way so that there is no current in the galvanometer, no deflection in the galvanometer. That means Ig should be 0. No deflection means Ig should be 0. Okay. So now let us apply, if Ig is 0, so now let us apply the Kirchhoff's second law to the circuit ABDA, AB. So you can see ABDA. So we are choosing this part ABDA. We are choosing this part ABDA. We will move along like this. So see how we are writing. So we are going in the direction of the current, so I1P plus I1P. In the direction of Ig, so it is plus Ig into G. And now opposite to the direction of the current we are moving. Okay, so it is minus I1 into R, which is equal to 0. Okay, apply the Kirchhoff's second law. Now we are applying the law in the loop BCDB. That means this is the way how we will move in the circuit. This is the way how we will move in the circuit. So see, we are going in the direction of this current. So I will write plus I1 minus Ig into Q. And then we are moving opposite to the direction of the current. So current is coming from here. Current is coming from here. See. So we are moving opposite to the direction of the current through the resistance S. So it is minus I minus I1 plus Ig into S. And now we are moving opposite to the direction of Ig. Opposite to the direction of Ig. So it is minus Ig into G equal to 0. Okay. Now from here, as I told you that if Ig is 0, so now the first equation becomes I1P minus I minus I1 into R. The first equation becomes this. Okay, or it is this. And the second equation becomes this. Putting Ig 0 in the second equation, we get this. So dividing these two equations, dividing this equation by this equation, so see what we get. I1 cancels, and then from here we can get the relation P by Q equal to R by S. So remember, this is the condition for a balanced Wheatstone bridge. Balanced Wheatstone bridge in which Ig should be 0, and this is the condition for the balanced Wheatstone bridge. Clear? Next. So as I have shown it, this is the balanced condition in which Ig should be 0. Clear? Now let us start the topic slide wire bridge or meter bridge. Slide wire bridge or meter bridge. So see, here is the meter rule starting from 0 to 100. That is why this, see, you can see the wire AB. You can see the wire AB. You can see the wire AB. It is of length 100 centimeters. Okay, and here is an EMF, battery used, and a key K, and here is the resistance R. You can see the R resistance applied here. You can see the S resistance applied here. And now what we will do is that from here we will take a wire connected to the galvanometer, and then this is a tap key. This is the tap key. This is the tap key. So what we will do, we will tap the wire AB at different points. We will tap the wire AB at different points, and note the galvanometer deflection, okay. We will continue to do that until and unless galvanometer deflection shows 0. We will continue to tap on the wire until the galvanometer deflection is 0. We will continue to tap the wire AB until the galvanometer deflection shows 0. That means IG will be 0. So watch here. Here is R, here is S. So this part, suppose on tapping at the length L, we get the galvanometer deflection 0. Okay. So I can tell you, so if this is L, so this part is 100 minus L. This part is 100 minus L. Okay. So let us imagine that for every 1 centimeter of the wire, the resistance is R. For every 1 centimeter of the wire, the resistance of the wire is R. That means for a length L, the resistance will be LR. So that is the resistance of P. LR ohms. So for 100 minus L, the resistance will be 100 minus L into R, and that is the resistance S. So we know that when IG is 0, the relation should be P by Q equal to R by S. So what is P? P is LR. And Q is 100 minus LR equal to R by S. So R and R will be cancelled. So S will be this. So this is how we can calculate the value of S. S means this is the unknown resistance. Mind it, this is the unknown resistance which will balance the meter bridge. Unknown resistance which is causing the balance of the meter bridge. Okay, so this is how we calculate the length at which the meter bridge will be balanced. That means IG should be 0. Next, please remember certain points about the meter bridge, certain very, very important points on which questions are asked about a meter bridge. So when the Wheatstone bridge is most sensitive when the resistances of all 4 arms, that means P, Q, R and S is the same. The Wheatstone bridge will be most sensitive when these values all are same. They all will be same. Then only the Wheatstone bridge will be more sensitive. Number 2 point. A meter bridge cannot be used to measure very high or very low resistances. Mind it, you cannot use a meter bridge for very high or very low resistances. Third, the balance position of meter bridge is not affected on interchanging the position of the battery and the galvanometer. That means, if you please watch the diagram, this is the battery, and this is the galvanometer. If I use the galvanometer here, and the battery here, that means it will not, the balance point L, length L, will not get affected. The balance point L, that will not get affected. So please note that the balance point L will not get affected if you interchange the battery and the galvanometer. Clear? Next, so let us discuss about another important topic, that is called the potentiometer. So it is so we have studied the Wheatstone bridge, we have studied the meter bridge, now we will study the potentiometer. So see the potentiometer, how this is the potentiometer. It starts from here A, and this is the wire up to B, 100 centimeters, up to this point 100 centimeters, then it is 200, from here to here it is 200, from here to here it is 300, and from here to here it is 400 meters. So this is the total length of the wire, which is used as 400 centimeters. Here is a rheostat, here is an ammeter, and here is a battery. So what we will do is, from here we will connect a voltmeter or a galvanometer. We will use a galvanometer here, and then we will tap on the lengths of the wire. Along the length of the wire we will tap till the galvanometer deflection will be shown as 0, till the galvanometer deflection will be shown as 0. Okay, so now let us start. We will keep tapping at different points till the galvanometer deflection will show the 0 marking. So first of all, the potentiometer is used for measuring EMF of a cell or potential difference between 2 points in an electrical circuit. I want to measure what is the potential difference between A and J. I want to measure what is the potential difference between A and J. So this potentiometer will help me to find out the potential difference between A and J. Okay, that is the use of the potentiometer. That means it will tell us, it is used for measuring the EMF of a cell or potential difference between any 2 points in an electrical circuit. So we can measure what is the EMF we are using, or what is the potential difference between any 2 points, suppose between A and J. What is the potential difference between these 2 points? That also we can measure. So on what principle does the potentiometer work? On what principle does the potentiometer work? The fall of potential. So see here, the fall of potential, this is the positive, this is attached to the positive terminal, as you can see. So this is, here the potential is maximum, and here the potential is 0. At B the potential is 0. So there is a fall of the potential. There is a fall of the potential along the length. As you go tapping, the potential will go on decreasing. The potential will go on decreasing till it becomes 0. The potential will go on decreasing till it becomes 0. Okay. So the fall of potential across any portion of the wire. So the more I go from A towards B, the potential will go on decreasing. The potential will go on decreasing. The potential will go on decreasing. Okay, like this. So the fall of potential across any portion of the wire is directly proportional to the length of the wire. So potential fall will be proportional to the length chosen across the wire, or V equal to KL. Well, K is called the potential gradient. K is called the potential gradient. So K equal to V by L. That means, so the SI unit of this will be volt per centimeter. Volt per centimeter. So this is the principle of the potentiometer. That means as you move along from A, the potential will keep on decreasing and is proportional to the length of the wire chosen. Proportional to the length of the wire chosen. So potential is equal to KL. Well, K is called the potential gradient. K is called the potential gradient. Okay. So It is the fall in potential per unit length. Fall in potential per unit length. That is the potential gradient. Now let's see few more things about this particular chapter. First of all, see, they have given that if the current is 1 milliampere, 1 milliampere is 10 to the power minus 3 ampere. So 1 milliampere means 1 into 10 to the power minus 3 ampere. So this is our current flowing through a potentiometer wire of length 4 meters. So the line length is given 4 meter, and the resistance of the wire AB, resistance of the wire AB is 4 meter. Find the potential gradient of the wire. So potential gradient is total potential by the length. So how do we find the total potential? Total resistance is 4, total length is 4. So the total potential will be I into R, which is 4 into 4, I into R. So I is given as 1 into 10 to the power minus 3 into 4, and the total length is given as 4. That means it is coming 10 to the power minus 3 volt per meter. This is the potential gradient of the wire of the potentiometer. Okay, this is the potential gradient. Next, determination of potential difference using potentiometer. So how, as I told you, that we can find out the unknown potential difference using a potentiometer. We can find out the unknown potential difference using a potentiometer. So let's see. Here what we will do is that, you see, this is the potentiometer wire being used here of length 100 centimeters. As you can see, this is the wire AB of length 100 centimeters. We have used a resistance R. This is the EMF of the battery being used. So first of all, what we will do, close the key K. This is the key K. Okay, now close the key K1. Close the key K1. This is the key K1. This is your key K1. So what happened? Current flows through R. This is the resistance R. When you close the key K and K1, the current will start to flow through R. This is the resistance R. A potential difference is developed across it. So across the wire AB there is a potential difference. Across the wire AB there will be a potential difference. Correct? Now tap the jockey J. So we will tap this jockey J and watch the galvanometer deflection shows no deflection. We will watch for no deflection. No deflection. We will watch for no we will keep tapping here. First allow the key to get closed. So current will start flowing from here. Current will start flowing from here. So there will be a potential difference created across AB. Now we will start tapping the key J until we see no deflection in the galvanometer. Okay. So let the length of the wire which you tapped is L. This is L. This length is L. Clear? So now what is the potential across this length? It is, we know potential will be potential gradient into the length. We know potential difference will be potential gradient into the length. Clear? Now let R be the resistance of the wire AB. The current flowing in the wire I is. Now what happens? See, let the resistance of the wire AB be R. Let the resistance, so RAB is the resistance of the wire. Okay. So now what is the current flowing in the wire? The current flowing in the wire. So the current flowing in the wire will be the EMF, total EMF by the total resistance here is R outside, R and small r are series, so this is the total current flowing. Okay, so this current when flows across AB, so what is the potential difference? This is the potential difference, because the resistance of the wire AB is R. Clear? Now the potential of the wire AB is R. So now what is the potential across the AB? That is KL. Potential across the wire AB is also KL. So using this KL is equal to, KL is also the potential across the wire AB, and which is equal to E by R plus R into R. So from here we are getting the value of K. We are getting the value of K. Clear? Now once we get the value of K, we will put in this V equal to KL. We will put it here, V equal to KL, and then we will get the potential difference across the wire AB. We will get the potential difference of AB. We will get the potential difference of AB, and this potential difference is the EMF E1. This potential difference VAB, and that is only E1. So this is how we calculate the unknown EMF. We calculate the unknown EMF. This is how we calculate the unknown EMF. Clear? So now let's see. So as I told you that the potential depends upon the length chosen. So if I choose two EMFs, E1, and suppose it has balanced at a length L1, so I will write E1 equal to KL1, and suppose now I am connecting E2 and it is balancing on a length L2. It is balancing on a length L2, so E2 will be KL2, and now dividing these we get this relation. This is how we compare the EMFs of two unknown cells. This is how we compare the EMF of two unknown cells. Clear? Now how to determine the internal resistance of a cell by a potentiometer wire? How to determine the internal resistance of a cell using a potentiometer wire? So see, this is the potentiometer wire AB of 100 centimeter length. Okay, and now we want to calculate what is the internal. Suppose this has been, first of all what we will do, we will first of all switch off this part and only allow the current through the EMF to the battery to go, and suppose that has been balanced at a length L1. So I can use E equal to KL1. First of all, I will close the switch K1, so no current will flow through R. The current will only flow through E1, and suppose it has balanced at a length L1, and we know potential gradient is K, so I will write E equal to KL1. Now what we will do is, now our target is to close, our target is now to close the key K1, to close the key K1, so current will also flow through this part, current will also flow through this part and this part. So now let the potential developed is balanced across the length L2. So I will write V equal to KL2. We will write V equal to KL2. Now dividing we get this length, dividing we get this relation. Okay, so this is the potential EMF of the cell is balanced on a length L1, and the potential terminal voltage is balanced at a length L2. So now what is the resistance, internal resistance? It will be the internal drop by the current. It will be the internal drop. So this is the internal drop. This is the internal drop by the current. So what is the current? Current is V by R. Current is V by R. Okay. So now using this relation, so we are getting this. So E by V was L1 by L2. So this is the relation for finding the internal resistance of any cell using a potentiometer wire. Clear? This is the relation for finding the resistance, internal resistance using a potentiometer wire. So first of all, let's see sensitivity of the potentiometer wire. What is sensitivity? It is the smallest potential difference that can be measured with its help. The smallest value of potential which you can measure using a potentiometer wire is called the sensitivity. The sensitiveness of potentiometer can be increased by decreasing the potential gradient. So you want to increase the sensitivity, you decrease the potential gradient. Okay, because potential gradient equal to V by L. So to decrease this, I have to increase the length of the wire. I have to increase more length of the wire. So if I choose more length of the potentiometer wire, if the length of AB is increased, then potential gradient will be decreased, and potential gradient decreased means sensitivity will be increased. Please keep this in mind. Clear? So this is what I was telling. By increasing the length of the potentiometer wire and by decreasing the current of the potentiometer wire, that means why the current? Because K is proportional to V. So if I decrease the current, then V will be decreased and K will also be decreased. So if K is decreased, S will be increased, sensitivity will increase, sensitivity will increase. So this is the concept used here. Now let us see difference between potentiometer and voltmeter. First of all, it measures the EMF. Potentiometer measures the EMF of the cell and voltmeter measures the EMF of a cell approximately, and this is accurately. Please keep in mind, this is accurately, not approximately. This is accurately. It measures the EMF of a cell accurately. Okay. While measuring the EMF, it does not draw any current from the source. And here what happens? It draws some current. It draws some current from the source. Third, while measuring the EMF, the resistance of potentiometer becomes infinite. Resistance of the potentiometer becomes infinite. Now here, while measuring the EMF, the resistance of voltmeter is high but finite, not infinite. Resistance is not infinite. Its sensitivity is very high. Sensitivity is high and its sensitivity is low. Fifth, it is based on null deflection method, and it is based on deflection method. It will only give me the reading, and this will give me zero deflection. Then only the sensitivity will be more. Sixth, it can be used for various purposes. It can be used only to measure EMF or potential difference. Mind it. Galvanometer can be, potentiometer can be used for many other things, but voltmeter is used only for measuring the potential or EMF. The balance point is obtained on the potentiometer wire if the fall of potential along the potentiometer wire due to the driving cell is greater than the EMF of the cell to be balanced. Okay, the balance point is obtained on the potentiometer wire if the fall of potential across the potentiometer wire due to the driving cell is greater than the EMF of the cell. That means the V should be greater than the EMF of the cell. Then only we can use the potentiometer wire. The balance point cannot be obtained on the potentiometer wire if the fall of potential across the potentiometer wire due to the driving cell is less than the EMF. That means this also I can tell if K the value of K here is greater than equal to EMF and here K is less than the EMF, then we cannot use the potentiometer wire. But here we can use that. If the value of the K is less than EMF, we cannot use the potentiometer wire. We cannot use the potentiometer wire. Clear? Now let us see some more examples using the concept of the chapter Kirchhoff's law. A battery of 6 volt, this is 6 volt, internal resistance 0.5 ohms is joined in parallel with another battery of 10 volt, internal resistance 1 volt 1 ohms. It sends a current through the external resistance 12 ohms. Find the current through each battery, how much each battery is sending the current. So let us start the sum using the Kirchhoff's second law, which says that the sum of the potential will be 0. Sum of the potential difference across a closed circuit should be 0. Using this concept, let us start. First of all, we are choosing the loop A E to B R. A E to B R. That means we are going like this. We will go like this. A E to B R. So now see here. In the battery E2, we are going from positive to see the direction how we will move. We will move like this. We will move like this. So we are entering positive to negative, so it is plus 10. Now we are entering in the inside the cell, there is a resistance 1 ohm. Okay, so inside the resistance, the cell we have chosen AE2, sorry, we have chosen this part. So first let us see. We have chosen this part and now see how we are applying. We are choosing this part. This is how we will be moving along. Okay, so we are coming out from the battery's positive terminal, so plus 10. Now over the resistance R we are moving, see, we are going like this. AE2, sorry, we have again I have drawn the direction wrong, so no problem. Let me draw the loop properly. So the loop says that we will be moving like this. We will move like this. Like this we will move. Okay, A E to B R A. So we are entering from the positive to the negative, that means it's plus 10, correct? Now we are entering, we are passing over the resistance in the direction opposite to the current. Current is coming like this, we are moving like this, opposite. So minus 12 I1 plus I2 current is going over it, and then we are also passing through the resistance, internal resistance 1 ohms, which is against the current direction, which is the minus I2 equal to 0. So from there we create this relation. Now let us choose the loop. Let us choose this loop. Let me choose the loop AE1 BR. That means AE1 BR. So we are moving like this, AE1 BR. We are moving like this. We are moving like this. So let us apply the rule. The rule says that you are going from positive to negative in the E1, so it is plus. And now you are going through the internal resistance in the opposite direction. Current is coming out, but we are going opposite, so minus 0.5 I1. Then we are moving opposite through the resistance capital R, which is minus 12, so that's why minus I1 plus I2 equal to 0, and we are making this relation. Okay, so now what we will do is we will solve these two equations, and then the first equation and the second equation. What we are doing is that we are subtracting the second equations, the first from the second, and so we are getting this relation. We are getting this relation. Okay, so now what we are doing, see, so I2 will, from here I2 is this, from here I2 is this, putting in the first equation, yes, in the first equation, putting the value of I2, so we are getting I1 as minus 2.727 ampere. That means we have taken the I1 in this direction, so it is actually coming negative. That means we should have taken it in this direction. We should have taken I1 in this direction. It has come opposite. Now putting the value of I1 again in this part, in this relation, we can calculate the value of I2. It has come positive. That means our direction assumed was correct. So this is the current. So the through the EMF E1, the current which is coming out I1 is actually 2.27 ampere, and through E2 the current which is coming out I2 is actually 2.86 ampere, and this is our answer. Clear? Next, let's see the next thing, friends. So what has come out here, see, let's choose the next slot. Okay, okay friends, so this is the next slot. As you can see, the figure as itself, you can see the complete figure is given to you. They are telling calculate the current through each cell and the potential difference between the ends of the wire EF. This is E, this is F. They are telling calculate the value of VEF. So first of all, let us choose our loop. Let us choose our loop A, E, F, D, A. So we are choosing the loop, this one. Okay, so this is the loop we are choosing. So as you can see, first of all, see the current distributions. Let the current coming out through the 2 volt is I1. So I1 goes like this. Let the current coming out through the 1 volt at the bottom I2. So I1 and I2 meet here, they go here. So I2 returns back, I1 goes there, and this is the complete circuit. So now using the first loop, and we are going like this from negative to positive. We are going from negative to positive. So that is why -2. The potential is -2 plus 1 I1. We are moving in the direction of the current through the cell. So plus the internal resistance is 1 ohms. Current is I1. So it is in the direction of the current. So which is plus I1. And we are moving from negative terminal to positive terminal. That is why it is -2. It is -2 volt plus 1 I1. And now through 5 ohms, we are moving in the direction of the current. So again it is plus 5 I1. Now through 10 ohms, we are moving in the direction of the current. Okay, that means again it is plus 10 I1 plus I2. Now through 2 ohm, we are moving in the direction of the current. So plus 2 I1 equal to 0. So solving this, we get this relation as the first equation. Next, so let's see the next thing, friends. Let me erase it so that I can show you the next part clearly. Okay, so see, in the next part we have chosen the loop. We have chosen the loop EFCBE. EFCBE. So we are moving like this. Closed loop, we are moving like this. So through the battery, it is negative to positive terminal. That is why -1. And it is from inside the cell, there is a internal resistance 2 ohm. So current flowing is I2. So plus 2 I2. Through 5 ohm, we are moving in the direction of the current. So plus 5 I2. Through 10 ohms, we are moving in the direction of the current. So plus 10 I1 plus I2. Through 2 ohm, we are moving in the direction of the current. So plus 2 I2, which is 0. So this is our second equation. Now what we are doing, second equation minus first equation. So we are getting this part, I1 equal to -14 I2. Okay, now we are putting the value of I1 in this relation, and we are getting I2 as -1/121 ampere. That means the direction of I2 should be opposite. The direction of I2 should be opposite because minus has come. Now putting the value of I2 in this relation, we get the value of I1, which is 14/121 ampere. So it is coming positive. That means we have taken the direction of I1 correctly. Now they asked me what is the potential difference across EF. So EF will be 10 I1 plus I2. Putting the value of I1 and I2, we get it is coming 1.07 volt. 1.07 volt is the potential across the points EF. Clear? So friends, let's see the next one. Next circuit. This is the circuit given. See, there is a 2 volt EMF, internal resistance 4 ohms, 1 volt EMF internal resistance 3 ohms, 4 volt battery internal resistance 2 ohms. So they are telling find the current through each cell. Find the current through each cell. Okay. So first of all, let us choose the loop A, E1, B, E2, A. That means we are choosing the loop like this. We are choosing the loop like this. We are choosing the loop like this. Okay. So let's see. So negative to positive in the cell we are going. So minus 2 volt plus 4 I1, current coming out is I1, current is I1 in the direction, plus 4 I1. Then current is entering in the positive terminal to negative, so plus 1 volt. Okay. Then current is going opposite inside the 3 ohm. So I will take minus 3 I2. So the loop is over, so it is 0. That means we have got this relation. Second, now let me show the second loop. So the second loop says that you have to go A, E2, B, E3, A, E2, B, E3. So I will choose to go like this. This is the loop. This is the loop. I will go. Okay. So inside the cell I am going from minus to plus, that is minus 1, plus 3 E plus 3 I2 because I am going in the direction of current. Next we are entering from positive terminal, so plus 4. We are going opposite to the direction of current through 2 ohms, that is minus 2 I3 equal to 0. So we got this relation. Okay. So now let's see the loop. Next loop. First of all, how will you understand how many loops to take? So see, we are using 3 variables, I1, I2 and I3. So since we have taken 3 variables, so we have to use 3 loops. 3 loops, otherwise we cannot solve the sums. Okay. So 2 loops we have already taken. Now A, E3, A, E3, B, E1. So we are choosing this loop. We will be choosing this loop like this, and we will start from here. So we are entering the positive terminal, that means it is plus 4. Then we are going opposite to the direction of current through 2 ohms, so which is minus 2 I3. Then we are going from negative to positive, so minus 2 volt. We are going in the direction of the current through 4 ohms, that is plus 4 I1 is 0, and we got this equation. So now what we will do is, now we will be, and see, another thing is that if I apply Kirchhoff's first law at the point A, all the currents are coming into the junction which is taken as plus. So I1 plus I2 plus I3 equal to 0, right? So from there I3 equal to this. Now what we will do from here, we will put the value of I3 in the equation number 2. We will put the value of I3 in equation number 2, and we get this relation. Okay. Now what we are doing is equation 1 minus 4 times of equation 4, 2 times of equation 4, equation 4 2 times, from equation 1 subtract that. So this is the 2 times of the equation number 4, and now from equation 1 minus equation this, we are getting I2 as this. Once we get I2 as this, we can put it in the equation number 1 in place of I2, and get I1. Now we know I2 and I1, so we can put it in this equation, which is I3 equal to minus of I1 plus I2, and we will get I3. So these are the currents which are coming out through the 3 cells. Okay, these are the currents coming out through the 3 cells. Clear? Please pause my video and keep watching them slowly so that you can understand the logics what I am applying. Please pause the video, slowly watch them, so you will understand how I am applying it. Clear? Next, let us see. Now see, this is a cube. This is a cube whose opposite terminals has been connected. See, opposite terminals has been connected. It's a cube. So let us take the resistance of, they have given resistance of each arm is 1 ohms resistance, because it's a cube of equal lengths. So let the resistance of each arm be 1 ohms, and they have used a battery. They have used a battery of 10 volt. 10 volt. So they are telling what is the equivalent resistance of the entire cube. So how to find out? First of all, let us take the loop ALK. See, this is the loop which we are choosing, ALKNE. That means we are going like this. This is our loop. This is our loop. Okay, so we are going like this. So first of all, watch here how the distribution of the current has been done. Watch here how the distribution of the current has been done. So because it's a cube connected to the opposite terminal, so there is a symmetry. That means there is a symmetry created. Please watch here. There is a symmetry created. If you cut the loop, if you cut the cube, if you can cut the cube like this, so there is a symmetry created. Okay, it will be symmetrical on both sides. That is why the distribution of the current will also be the same on both the sides of the cube. The distribution of the current will also be same on the both the sides of the cube. So now watch what we are doing. Let the total current coming out be 6I. So we are distributing the 6I as 2I on this arm and 2I on this arm. Correct? Again 2I on this arm, 2I on this arm. Now see, so in this it goes 2 arm to 2I, 2I and 2I. Now what happens? So in this part 2I has come, so it will again now distribute. This is 2I coming, so it has distributed as I and I. As you can see, I and I. Similarly, this 2I will distribute as I and I, and similarly this 2I will get distributed as I and I. Okay, because it will be equally distributed in the parts, as it is a symmetrical figure, as it is a symmetrical figure. So now after this part, so see the current, this I comes here, we meet as 2I. Again this is the I coming, so this is the 2I. Again you see this is the I coming, so this is the 2I. Now 2I, it is the 6I. Clear? It is the 6I which is being again returning back to the battery. So now let us get started. So we have chosen the loop, and now see, let's get started. So it will be from negative to positive, so minus E, and then I will go along this, so it will be 2I, it will be 2i into the 1 ohms, because each arm is 1 ohm, and now along this, so it will be I into 1 ohms, and now along this it will be, so this is our path of going along 2i, so it will be 2i into 1 ohms equal to 0. Clear? Which is coming E equal to 5i. Now instead of the cube, suppose I connect a resistance R. I connect a resistance R. So what will happen? This is 6i coming, and this is E. So how will I write E equal to 6i into R? But E was 5i, so 5i and this I cuts, so R equal to this. That means my equivalent resistance will be this. So what is the current coming out now? Current coming out will be the potential by the resistance. So 10 volt by 5 by 6, it is 12 ampere current coming out through the cell, which is E of 10 volts. Clear? So now friends, let's look into the next sum. What is it all about? The next sum, which is this. So as you can see, this 12 equal wires, each of R ohm, each of the wires, each of the arms of the wire are R ohms, because it's a cube, form a skeleton. Find the resistance between the corners of the same edge. Now we are taking same edge, so the distribution of the current will not be, the distribution of the current will not be symmetrical. The distribution of the current will not be symmetrical. So let us first see. So watch here. Here is the EMF E. Let the current coming out be I plus 2I1. I plus 2I1 is the current coming out. Mind it, it is not symmetrical. Not symmetrical. The previous one was symmetrical. This is not symmetrical. So current distribution, please watch here. It is I plus 2I1, and let I1 go to this part. I1 go to this part, and I goes to this part. Okay, this is how the distribution now starts. Now out of this, as you can see, let I2, let out of I1, I2 go this, so the remaining current I1 minus I2 will go on this part, right? I1 minus I2 will go on this part. Similarly, so watch here, this is I1 minus I2 coming this side, this is I2 going like this, correct? Now this is the current I1 coming. Now watch one thing, this is the current I2 on this, on the arm BC. So diagonally opposite is the arm LK. Diagonally opposite is the arm LK. This also should carry the same current. This also should carry the same current. So I2, that means out of I1, I2 goes on this side. So I1 minus I2 should go on this side. I1 minus I2 should go on this side. Now opposite to LM is the thing KN. So to balance this, see, I1 minus I2 should come on this side. I1 minus I2 should come on this side, right? Please understand the distribution of the currents, because it's very important. So till here we have discussed. So now let's see, this is I1 minus I2 and this is I1 minus I2, so this is 2I1 minus I2. This is 2I1 minus I2. Now watch here, I1 goes this side, so I1 should go, to balance it, I1 should go on this side. I1 should go on this. This is I1 going this side, so I1 should go on this side, right? Now I'm discussing the direction of the current. Friends, please follow along with me how we are doing it. So if you can see the distribution of the currents in each arm, ultimately watch here, the current which is coming out from here, this and this will get added, and it comes out as I1. It comes out as this I plus 2I1. So whatever current was entering, now this same current has been received back. Clear? Now, so let's watch here. If I take the loop ALKEA, ALKEA, that means I am taking this loop ALKEA. This is the loop I am taking. Okay, so we are going from negative to positive. That means minus E. Then we are going along AL. AL has a resistance R. So in the direction of the current, so plus RI1. Now LK in the direction of the current, so RI2. Now sorry, we have to go along this direction. 1 minute. So it is this direction D, that means this direction. Yes. Okay, friends, so this is the direction. So now let's see. So now we have to go along KD, so it is plus RI1 equal to 0. So from here we get, this is the first relation. This is our first relation. Now we are going along the loop. I will show you the second loop, which is, so see the loop ABCDA. That means we are going like this. We are going like this, ABCDA. So in the direction of, from A to B, in the direction, that means positive RI1. In the direction from B to C, that means positive RI2. In the direction from C to D, so positive RI1. Now opposite to the direction, current is coming like this, we are going like this. So opposite to the direction of current from D to A, so it is minus RI. So that is the loop which we have created, and now that is the equation. Okay, so that is the equation. From here we get, this is the relation. Now we will see the loop BCN MB. So watch here, BCN MB. That means we are using this loop BCNMB. We are using this loop BCNMB, and we are going from in this direction. So first of all, from B to C, it is in the direction, so RI2. Then C to N, it's opposite direction. C to N is opposite, current is going like this, we are going like this, C to N, opposite direction, so minus. Now N to M, opposite direction, so it is also minus. N to M is also opposite direction, okay, it is minus. And now M to B is also opposite direction, so it is minus. So from here we are getting the relation. See, that is, we have done equation 2 1 minute. So friends, yeah, from here you see we are getting this relation. So which is I1 equal to 5I2 by 4. Now what we will do, we will put this in equation 2. So see, which is, this is equation 2. In the equation 2, in place of I1 we have put 5I2 by 4, and we are calculating the I2 as 2I by 7. Okay, so I2 is 2I by 7. Now put the value of I2 here. So we, in this relation, put the value of I2. So we will get, this is I1. This is the value of I1. So we got I1. So what was the total current which we have taken? That is I plus 2I1. So this is the total current. I1, putting the value of I1, this is the total current. This is the total current which we have got. Now let the equivalent resistance be, R. So see how to draw. Let the equivalent resistance be R. That means I will take it like this. So this is the equivalent current coming out, which is 12I by 7. Okay, and this is the E. So then how will I write? E equal to 12I by 7 equal to 12I by 7. This is how I will write. 12I by 7. Correct. Now into R. So this is E, the value of E. Okay, so from here, see how to write in this equation. E equal to 12I by 7 into R. We have done this. Now from here, see, let the total resistance be R. What is the current coming out? Let me please watch here. The total current coming is, they have given each resistance is of 12 ohms. Okay, I think some value I am missing. ER 121I into R, total equivalent resistance. Okay, correct. Yes. Yes. So please watch here. Now, so in equation 1, E equal to 2R I1 plus R I2. That means we are putting the value of I1 and I2, and we are getting the E as Ri. E as Ri. Now putting that E as Ri in the equation, we are seeing that I and I cuts. So this is the equivalent resistance of the whole circuit. This is the equivalent resistance of the whole circuit. Clear? This is the equivalent resistance of the whole circuit. So let's see, friends, next. Again watch, here is a loop given. As you can see, EMF given I, current coming is 2I. So I and I distributes, here is I, here is I, which is 2I getting distributed. Okay, from I, here I have taken I1, so here is I minus I1. Clear? Now if here is I1, I have to take I1 here diagonally opposite, and here if it is I minus I1, then here it should come I minus I1. Okay, now from here, this is I coming, I1 gone here, so definitely I minus I1 will go this side. From I, if I1 has gone this side, I minus I1 should go this side. get added to this, and the current coming out is 2I minus I1. Okay, from 2I minus I1, if I minus I1 goes this side, so this is the part left, I minus I1. Clear? Now I1 and I minus I1 added up gives you I. So I comes here, I1 comes here, so these two get added and it gives you I. Now I plus I gives you 2I. So this is the distribution of the current in the circuit. And now let us start the applications of the Kirchhoff's law. Let's start the applications of the Kirchhoff's law. So Kirchhoff's law, they are telling that 11 wires each of 2 ohms in complete Q, find the resistance between the ends. Okay, so let us apply the loop in ADFKEA. So see, this is ADFKEA. That means we are going like this. We are going like this. Okay, so first of all, resistance of each arm is 2 ohms. So from A to D, first we are going from A to D. First we are going from A to D. So see this. So A to D, resistance is 2 ohms, current is I. So it is in the direction, so 2I. Next from D to A, D to F. So we are going in the direction, resistance is 2 ohm, current is I1, so 2I1 plus. Then we are going from F to K. F to K again in the same direction of the current, so it will be 2I plus. Now we are going minus to positive in the battery, so negative terminal to positive is negative minus E. So we are getting this relation. So this is one relation. Now let us apply the Kirchhoff's law again to this part. CGFD, CGFD, we are applying to this part, CGFD. Okay, so first we will go from C to, we will first go from C to D, C to D, C to G. So in the direction of the current, resistance is 2 ohm, so 2 into the current, this is the relation. Then we will go from G to F, in the direction of the current, again 2 into this is the resistance and this is the current. Now we will go from F to D, which is against the current, so minus, potential difference will be negative, so minus 2I1, which is 0, and then we are getting this relation, I1 equal to 3 by 4 I. So now instead of I1 I will put 3 by 4 I, and we will get the EMF 11I by 2. So now let us assume that, so this is the, and let us assume that instead of the cube, the equivalent resistance is R. So the current coming out is 2I. So E, so we can write E equal to 2I into R. But E is 11 IR. So using this II cuts, so R equal to 11 by 4, which is 2.75 ohms. Clear? So friends, let's see the next one. So the next one shows that this is the circuit. Watch here, this is the circuit of the next one. They are telling determine current in each branch of the network. Determine current in each branch of the network. So first of all I have chosen, so see the circuit diagram, chosen ABCA, ABCA. So this is the circuit diagram we will choose, this ABCA, ABCA. So we are going in the direction, first we are applying, So we are applying first from A to B. A to B is in the direction of the current, so positive 4 into this. Then we are going again in the direction B to C, in the direction of the current, in the direction, so again plus. Next we are going opposite, again in the direction of the current, and from negative to positive, so in the direction of the currents, so it will be 1 into I1 and minus 10. Using this we get this relation. Now applying it for the second loop. So see, let us apply the second loop here. Let us apply the second loop, A B E D A, A B E D A. That means we are applying in this part, in this way. In this way we are applying the loop in this way. Okay, A B E D A, closed loop. So watch here. That is, first of all, current is going from A to B. Current is going from A to B in the direction, so positive. This is the resistance into the current. Next we are entering B to E, which is positive to negative, so it will be positive plus 5. Next we are entering from this, so no resistance. Next we are entering from D to A, opposite to the direction of current, which is negative, so minus 4I3, and solving this we get this relation. Okay, so now applying the third loop, because there are 3 variables in the sum, so we are using the third loop. So what is the third loop? Let's see. ACDA, we are using this loop. ACDA. Okay, so first of all we are entering from batteries positive to negative. We are entering batteries positive to negative, so plus 10. Then we are going from A to C, which is opposite to the current, so minus 1I1. Next we are again going opposite to the current from C to D, opposite to the current we are moving, so minus. And next we are going again D to A, opposite to the current, again minus. So we are getting this relation. Now how to solve these equations now? So let us see how to solve the equations. We did equation 1 plus equation 3, we are getting this. If I add equation 1 and equation 3, we will get this. Now I1 I know, so in equation 2 I am putting the value of I1 and getting I3. Getting I3. In equation 3, putting the value of I1 and I3, I am getting the value of I2. I am getting the value of I2. Okay. They told calculate the current in each branch. That means in every branch AB. So what is the, in the branch AB, how much current is going? I1 minus I3, which is coming this. In the branch AC, current flowing is I3, which is this. AC. In the branch AC, current flowing is I1, which is this. In the branch BC, current flowing is I1 plus I2 minus I3, which is this. In the branch CD, the current flowing is I3 minus I2, which is this. That means in this way you can find out the current in every arm of the circuit. Every arm of the circuit we can find out the current, because we know I1, I2 and I3. Clear? Friends, next move on to this sum. So let's see what is this sum telling about. Two unknown resistances R and S. You see, this is R and this is S, are connected in the left and right gaps of a meter bridge. That means this is 100 centimeters, 0 to 100 centimeters. Okay. The balance point is found at a distance of L1. This is L1 and this is 100 minus L1. 100 minus L1. Okay. Now, so what can I say? That we already did P by Q in the balance condition. What will I write? R by S equal to L1 by 100 minus L1. Already we have done a relation like this. Next is, now they are telling, now we have applied, that here they are telling that we have connected another X in parallel. We have connected another X in parallel. So what is the net resistance here? Net resistance here will be this Sx by S plus X. How we are getting this? We will do 1 by S plus 1 by X. Okay. Net resistance we are finding. So Sx by S plus X. So it is the reverse of this. So the resistance will be Sx by S plus X. This is the net resistance here. So now let the balance point be obtained at L2 and this is 100 minus L2. Okay. So how will I write now? R by net resistance equal to L2 by 100 minus L2. So now we are dividing equation 2 by equation 1. So see how we are dividing it. This is our equation 2 and this is our equation 1. We are dividing it. So these all cut. So we are left with this part. S plus X is this relation. Okay. We are getting it. So S by X plus 1 equal to this. So S by X equal to this minus 1. So from here S by X equal to taking the LCM. So this is the unknown resistance X which should be connected with S. This is how the unknown resistance X should be connected with S. Okay, to obtain a balance point. Next, see friends, they are telling in a meter bridge a resistance R is kept at the left gap. Okay, when R1 and R2 are connected in turn in the right gap, the balance point is obtained at 60 centimeters and 50 centimeters from the zero end. Okay, so suppose when I connect R1, what will happen? It is the balance point is at 60 centimeters. So I will write R by R1 equal to L by 100 minus L. So it will be 60 by 100 minus 60, which is coming, R by R1 is coming 3 by 2. So R1 is coming 2 by 3R. Now when we connect R2, the balance point is obtained at 50 centimeters. So I will write R by R2 will be 50 by 100 minus 50. So R is coming equal to R2. R is coming equal to R2. Now they are telling, if I connect R1 and R2 in series and then in parallel. So see, in series, the net resistance, so it is R by the net resistance. What is the relation? As I told you, R by S will be L1 by L2. This is the relation. So let us see here. So when I connect R1 and R2 in series, they become R1 plus R2. So this is R1 and R2. So this is coming 3 by 5. L by 100 minus L. So L is coming 37.5 centimeter. That means when you connect R1 and R2 in series in the position of S, the balance point obtained is at 37.5 centimeters. And now when you connect R1 and R2 in parallel, so what is the net resistance coming? 1 by R1 plus 1 by R2. This is, put the value of R1 and R2, you get the net resistance as 2 by 5 of this. So the R by the value obtained when they are connected in parallel, let the balance point be obtained at L. So we are getting 5 by 2 from here, we are getting L as 71.43 centimeters. That means when, so first of all we found R1 and R2, then they are telling, please watch this figure, in place of, when, suppose imagine this is your R1 and this is your R2, and if you connect them in parallel, what is the balance point? If you connect them in series, what is the balance point? This is the sum all about. This is all the sum about. When you connect them in series, how to do it, and when you connect them in parallel, how to do it. And what is this R? R is the resistance which they are telling is actually this. This is the R, and R1 and R2 will be connected first in series, then in parallel. So they are telling what is the value of the balance point obtained in case of series and in case of parallel. So friends, with this we have come to an end of the chapter 2, which is about the Kirchhoff's law and its applications, and I hope that you have understood. I would request you, please go through the video very carefully, because it's a tough chapter, it is a very conceptual chapter, so please go through it properly, and please pause the videos and watch how I am discussing the things, then only you will be able to understand. Okay, please don't go through in a hurry, go through them in a very slow manner, and try to write down on your own also the clues and the tricks which I am discussing with you, then only you will be able to understand them. Okay, so with this we complete the Kirchhoff's law chapter 2, and then I will be completing the next part of this also very soon. And so one request from my side, please like my channel, it's Parijat Sir Classes. Parijat Sir Classes, please like, share and subscribe my channel so that I can make more and more videos. This is complete notes of, I'm again telling you, this is the complete notes of the chapter 2 electricity. You don't have to make any further notes of your own. You please study this and then it will be enough for you. Okay, so it's again once more thank you from my side for watching the video. Please keep subscribing and keep sharing my video as much as possible. So it's all from my side now. So thank you and goodbye.